Hello, dear students. Welcome on our first unit, lecture 1 in electrical drives. So, in our previous lecture, we have discussed what is the syllabus, what are the COs, what are the POs, which we are going to achieve through electrical drives as a subject. Electrical drives is an elective as discussed in our previous chapter. So, today, let's stop with a very basic thing, that what is the main heart of electronics, or what is a part of electrical drives. Now in this, motor can be run without drive, with drive. Now what is the basic difference with driving with a drive or without a drive? We know we use dual starter, that is direct online starter, as we have learned in control system components. But the only problem with dual and star delta is we can't achieve very precise speed of my drive or of my motor. That means if I want to run with 1440 as 1440 rpm, it is not possible for me to drive it without a drive, to drive a motor without a drive. What will I do if there is no drive, dual starter or star delta starter? What will happen if I press the start button? It is going to run at the maximum speed, no speed control with it. Now if we use this kind of devices in our blowers, in fans, now if my temperature of my room is controlled, what is the need of driving that fan or the blower? No need. So in that case, I just directly want to switch off the fan. Yes, but what happens again? The temperature goes change, it again shoots up, and again I want to restart the fan, but the fan will be having some inertia, it will waste some energy again in restarting. So instead of that, what we do, we go for electrical drives. In that, the power electronic converters take care to maintain a speed. As soon as they will take sense from the actual output that whether the output is reached, okay, reduce it. Okay, whether it is increasing, again reduce it. If whether it is reducing, again increase it. It will take care as our AC works. Yes, we know that if temperature rises, it will slow down if you want to control the cooling. And if it's heating, temperature drops, we will increase the temperature by AC. The same happens with our drive. Okay, in our vehicles like cars, what happens if this road changes, road actual physical things changes? If it's a rising slope, yes, we need to increase the acceleration. Yes, that means we are going to drive more power. If it's steep descent, we want to reduce the power, it's automatically going to take this change, that my speed has to be reduced. Now that can be taken care with an electrical drive. And what is this a future of electrical drives in our automobiles? Okay, in our electric bikes, all these are having a electrical drive inbuilt in them. Okay, so what is that drive composed of? It will having some input source, AC, it can be DC, it can be unregulated. Mostly in India we have AC, we don't have DC power supplies because it's really dangerous to handle DC source. If it's low voltage, it's okay, but if it deals with high DC voltage, then it's really very risky to handle DC source. It's an unregulated power supply. Okay, it's available everywhere. Then there is a power electronic converters. Then we have a load, that load can be AC motor, AC DC motor, and I have a controller. Now what for the controller is there, as I previously explained, to take the control actions, to increase the speed, to decrease the speed, to increase the temperature, to decrease the temperature. Yes. Now, a field of electrical engineering that deals with the application of power semiconductor devices for the control and conversion of electric power. Power semiconductor devices, what they will be comprised of, you all might be knowing. The first one is diode, then the SCR, then there is a triac, then I think there is a IGBT, there are MOSFETs, there are FETs. Okay, so these are the semiconductor devices. You might be knowing that they are the switches. They are nothing but the switches, and based on the gate applied voltages, they are being operating in their operating ranges. So this is going to be a control action. What is a conversion? Now the power semiconductor switch are going to convert. For example, I have a rectifier. What is the rectifier built of? A diode. It can be a SCR again. That is, it is going to convert the AC power to DC. What applies vice versa? It's going to invert from DC to AC. Then there will be inverters. Then inverters can be DC to AC. There can be of SCRs. They can be diode. No, they can be diode. That can be SCRs or IGBTs or MOSFETs. Yes. So these are the power semiconductors. So whatever we are going to learn electrical drives, the heart is power electronic converters. If you are through that, nothing is going to happen. If we are very familiar with the power electronic converters, and it's really simple to understand what is a drive. Yes. Now, as discussed, there is why we go for power electronic devices or why we use the semiconductor switches, because ideally there is loss zero when it is on and when it is off. Now see, in the picture they are showing that when the switch is on, then the voltage drop is zero but the current is flowing. When the switch is off, what happens? There is a voltage but there is current is zero. And what is power? Power is voltage into current. So the power loss is ideally zero in this electronic switches. As discussed, it's diode, the SCRs, the triac, then MOSFETs, and the IGBTs. These are the power switches. Ideally, it is lossless. These are the sensors. This is on, and these are the capacitors, resistors, inductors. Okay. Why there is a need of electrical drives? About 50% of electrical energy is used for drives. It can be either used for fixed speed or variable speed. This is the answer why we need a drive. I want to drive some things at fixed speed. I want to drive some things at variable speed. You take an example of a mixer motor. We are changing speed. Yes, we want to run at 1. Okay, the knob is at 1. We want to run at 2. It's again 2. But it is fixed that at 2 I will be having this voltage, at 3 I will be having this voltage. Same applies to my fan. But the same doesn't apply to my car, because the car is not working on knobs. Yes, there is a jerk. I don't want such kind of jerks in my automobiles. So in that case, I need very precise control of my speed, very precise ascent and descent of my speed, that is increase or decrease of the speed, that even a person we should not know what is whether there was a decrease in speed or whether there is an increase in speed. A very simple example, just a part of fun. When we landing and when we take off in an airplane, what happens? Do we feel that the speed was increasing, the speed was decreasing? No, we just feel when we touch the ground there is a jerk, but we directly don't when it is running at its maintained speed. If there is slight change in the speed also, then too we are not understanding whether it is happening in the airplane or not. So this is where electrical drive actually plays a very vital role. Now, variable speed drives typically used power electronic converters to supply the motors are DC motors, AC motors, switch reluctance motors, BLDC motors, so AC motors are induction motors, and permanent magnet, switch permanent magnet, I think it is split motors or all that. Okay. So till this it was explained that power electronic converters are being used. The takeaway message from the previous slides was the power electronic devices are being used right now in electrical drives. Then what was the previous scenario? How was the speed being controlled? Because before also there was a speed controlling applications, there was a vehicle, yes, then how it was driving. So in that purpose, what is the classical way was there was an AC motor, because AC supply was available before the advent of power electronic converters. Huh? The AC source was available, then this AC motor used to be running the DC generator at a fixed speed. This DC generator was separately excited. So by using this variable resistor and this power supplies, I can change the DC generator speed and I can get a variable DC here. The voltage will be changing and the DC variable voltage will be available. This will be fed to this DC motor's armature and this will run my load at a variable speed. Yes. So for controlling just a single load, I need a AC motor, I need a DC motor generator and DC motor. So in these, if I had 10 conveyors in my factory, what will happen? So 10 AC motors, 10 DC motors, 10 generators. It was really bulky, it was inefficient, and it's really inflexible to have such kind of devices. So this was a classic electrical drive for variable speed application before the advent of my power semiconductors. What did replaced? पावर इन, yes, there is a power in, ये तो है, ये तो नहीं है, तो ये कहाँ से रिप्लेस हुआ? By power electron converters. Now this is there, yes, this is there, but the DC generator, the AC motor was completely being replaced by my power electron converters. And by this controller there was an actual feedback which was being taken. That is, if I want 50 rpm speed, the motor will be running at 50 rpm speed. I was very sure that yes, it is going to maintain the speed. It was related to speed. But what happens if I want to cut something? That if I want a length of 10 mm only, so my drive has to cut, my conveyor has to stop at 10 mm distance. So at that kind also I did had a feedback of whether what is the position, that is called position control electrical drives, and it was only possible due to this power electronic converters, the feedback devices, and the control action being taken by the controller. Yes. So this application is very common, you all might be knowing. In a well, yeah, nearby well, we have a power supply, we have a motor, and we have a just dual starter. We press the green button, the motor starts, the pump starts pumping the water, but this loss is huge. There is a valve at valve position, there is loss, and in the pumping action there is a loss. So mainly there is a very huge power loss. But what about variable speed drives? I have a supply, I have a power electronic converter, there is a motor. So this power electronic converter will take care of all the thing of the pump, and so the power loss will be loss. So it's really very low power loss compared to this one. There will be a power loss, no issue, there will be surely a power loss, but it will be very less than that of my constant speed variable speed drives. Now example of this is fixed speed and variable speed. It's very common. We need to highly use these two types of fixed drives and variable speed drives. Now you had a topic in your unit, history of drives, as we are going to answer the same question right now. And also we have state of art of drives. So these two actually go hand in hand. So before that, what is we will just take a look of AC drives and DC drives. What is the overview of AC drives and DC drives? Electrical drives that use DC motors as the prime movers are the DC drives, and those that use AC motors as the prime movers, they are the AC drives. So what is the drawback of DC drives? Regular maintenance is required, heavy, expensive, and speed limit. Easy control, decouple control of torque and flux is very easy. What is the case of AC motors or AC drives? Less maintenance required, yes, because they are DC motors, you all might be knowing there is a brush, carbon brushes, then it's heavy, and we need a regular maintenance of DC motors. Whereas in AC drives, less maintenance is there, light, they are very light in weight, and less expensive and high speed is achieved with AC drives. But there is no coupling issue is always there in AC motors. Now let's begin with state of art, or what is history of DC, AC and AC drives. So before the semiconductor devices were introduced in 1950s, less than 1950s, AC motors were used only for fixed speed applications, and DC motors were used for variable speed applications by using that very bulky assembly which we have learned in just previous 2 to 3 slides. After the invention of semiconductor devices in 1960s, we started using AC motors in variable speed applications as well. But then too, there was a problem of coupling between flux and torque control, then application limited to medium performance applications like fans, blowers, compressors. Still, high performance applications like elevators, tractions and servos, they were dominated by DC motors only till 1960s. In 1980s, the scenario was completely changed. AC motors started running at high performance applications, elevators, traction, servos, and since the converter started decreasing in the price, yes, cost of microprocessor semiconductor started decreasing in AC drives. 1980s. This is how the scenario was. In 1990s, 60% was AC, 40% was DC, 70% was AC, and 30% was DC. In 1995, in just 5 years. In next 5 years, in 2000, we have 75% AC and 25% DC, and in 2005 we have AC 80%, 20% DC, and this is again decreasing day by day. This is how the state of art, that is the situation was emerging, and finally we had in the age like AC drives are just going to dominating DC drives. DC drives are getting absolute, and we are dealing with only AC and AC drives. This was all about our first unit, first few things. In the next session, we are going to learn what is the basic block diagram of AC drive and what are the parts, and also we will have a focus on how microprocessor control of a AC drive is DC drive and traction drive is being done. I hope you have understood. If not, please let me know in the comment box. Thank you for watching.